All right, I'm gonna go through these problems relatively quickly. I'll try to clarify anything that seems confusing, um, but do suggest asking additional questions if possible, obviously depending on time. So, in this first problem, you have a boy running off the cliff, horizontal velocity v0. We've already talked about this one. Basically, you're asked to derive an expression for the horizontal displacement, right? So this kid's gonna travel parabolic path like this, and it's going to land some distance away from where he initially jumped off. We're going to call that x. And so the position, according to our kinematics equation, works out like this. So plus 1/2 a t squared, right? Right away, we need to just recognize what's zero in these terms, because we know that there's no acceleration in the x direction, right? So the only acceleration in these situations is downwards due to gravity, and so we can eliminate any acceleration in the x direction. We can also set our x0 equal to 0, so we can make that a zero term as well, right? So we're saying that here at the starting point, x is equal to 0, and then at the end here, that's the displacement that we're looking for. So our basic equation is just that, x is equal to the velocity that he jumps off at, and then times the time it takes for him to actually land on the ground or in the water in the lake. But time is not one of the constants that's listed here, right? We need to make sure that whatever values are in your expression are only the ones that are given in the problem, and any physical constants like g, which is pretty much the only one we've discussed so far. So we need to look at the y direction. In the y direction, right, our values are some initial height plus his original velocity in the y direction minus 1/2 gt squared. We can assume that the initial height is h, right? So we'll say that at this point that y is equal to 0, and so his original position was at h. So our expression starts with h. He has no velocity in the y direction when he jumps off. You can see it's just a horizontal velocity. It has 0 velocity in the y direction. So that term is eliminated from our equation here. And then we can just leave the acceleration one with negative 1/2 gt squared. As far as the y value, the final position, he's jumping from h and then landing here at y equal to 0. So when we set y equal to 0 there. And then we solve this for time. So we move the negative value over to the other side, so we can have 1/2 gt squared is equal to h. And then we kind of eliminate all the terms on the left side that aren't t, right? So we multiply by 2 to get rid of the 1/2. We divide by g, get rid of the g, and then we square root the whole thing to get rid of the square, right? So our final expression here, sorry, do that. Final expression is that sorry, I should be doing this to the other side as well. It's 5 times 2 the g, and then square root that. My final expression is that t is equal to the square root of 2h over g. What's going to happen is that value, this expression here, is going to be plugged into the t value in our first equation. So x is really going to be equal to the original velocity that he jumps up at times the square root of 2h over g. Okay. You're asked to select the relationship that describes the time that the boy hits the water with to the rock at the time it's the water. And I want to make sure that this is clear, that any object that is free falling, whether it is moving at a horizontal velocity initially, or if it's just dropped stationary like this, they both gain velocity in the y direction at the same rate due to gravity accelerating them at the same rate. If they both have to travel the same height, then they're accelerated for the same amount of time. And so their velocities their height, their displacement, and their time to reach the ground here, or the water in this case, would be the same for both. Right? Two objects falling, but they have horizontal velocity or not, will always have the same time to fall from the same height. Okay, so if we were to describe this, a reasoning, basically, since all conditions, including the time, sorry, not the time, the height and initial vertical velocity are equal for both, it will take the same amount of time to accelerate both to the lake from a height h. You're asked to draw the horizontal component velocity for both of these. Since the rock is just being dropped, it's not being thrown horizontally at all, its velocity would just be 0 the entire time. This is for the rock. And then for the boy who runs off the cliff at a horizontal velocity, v0, right? This is for the boy. His velocity never changes, right? It doesn't increase or decrease. His horizontal velocity remains constant the entire time. All right, for D, select the correct relationship compared to magnitude of the landing velocity of the rock to the landing velocity of the boy. So what's happening is that when the rock falls, right, it continuously speeds up. And eventually, when it hits the water, it's going to have its highest velocity. Okay. The boy, on the other hand, so I'm going to draw this boy sort of a solid shaded circle, has an initial velocity in the x direction, but it's also going to be speeding up towards the water because of gravity, right? And so their position is moving sideways, but it's also accelerating at the same rate that the rock is in the vertical direction. Right, so by the time he's about to hit the water, his velocity in the y direction is the same as the rocks, but there's also the added component in the x direction for the boy, right? So the velocity for the rock is entirely the vertical velocity. The boy has the same vertical velocity, but he has an added velocity in the x direction. And velocities, because they're vectors, can be added in different directions. And so vectors, two velocities that look like this would just equal velocity that that would look like this, right? That would be equivalent to both of those velocities combined. Just think of it like traveling to the right and then traveling down as the same as traveling as at a diagonal like this. Same thing happens with velocity. These vectors can be summed. And so this velocity vector here would be greater than just the vertical and just the horizontal, right? It's a combination of both. So the boy has a greater velocity than the rock. And so we would try to describe this, specifically, the only things you really have to worry about are that both accelerate to the water at the same rate. And so gain the same Vertical velocity. But the boy maintains a horizontal velocity because there's no acceleration in the x direction. Due to no acceleration in the horizontal. Thus, at the surface, the boy has a greater velocity that's pretty much it. That's clear enough explanation to get full credit.